Well, thanks a lot for inviting me, for giving me this opportunity. Last time I participated in the program, that was like 5 or 6 years ago. It was a similar problem, and very good memories from that time. This time, unfortunately, I could not come, but
sorry, we are hearing very low voice. So can you speak up a little bit, or maybe being
just
closer?
A second. Let me try. Let me try. How do I more? You know, I wouldn't like to touch anything really. Audio settings. Just a second. Okay, let me try to approach to the computer. Is it better like this?
Yes.
Okay, good. Okay, so I'm going to talk about a problem that we considered with my postdoc, Andrea Tononi, and my student, Jules Givois. Basically, it's about binding of heavy identical fermions by a single light atom. So this is okay. This is a well-defined problem where you experience a competition between two factors. One is that heavy atoms, the identical fermions, they don't like to be bound to anything. This Pauli exclusion principle does not prevent, or you can say that the kinetic energy prevents them from binding. And the other factor is this attractive exchange potential that comes from the light atom, who likes to be surrounded by heavy atoms because it likes to hop. It gains energy on that. So the simplest formulation of the problem is the free space, non-relativistic, with zero range interactions. And it's parameterized by the space dimension, by the number of heavy atoms, and the mass ratio. And the dimer size, or the scattering length between the light and heavy, it can be scaled out. It can be set to 1. Okay, so the first kind of, you know, the object that accumulates most of this physics in the simplest manner is the Kartavtsev and Malek trimer, which arises from the p-wave attraction of the atom to the dimer, which with increasing the mass ratio increases, and at the critical mass ratio 8.2 you have a bound trimer state. Okay, it depends on, well, okay, there are ways of, okay, this is the object that has 3 spin angular momentum L equals 1. So you can consider this something rotates, atom rotating around the dimer, or you can consider this orbitals like px, py, and pz. The point is that there are 3 degeneracy in this formulation. There are 3 trimers like this. Okay, so this object is so fantastic that I usually, you know, I present this Born-Oppenheimer explanation because it gives you a physical picture. So in this formulation, you fix the heavy particles, and you find the energy of the light, the wave function, and the energy of the light atom in this field. So this is plotted here. This is the energy of the light atom. You see, it likes when the heavy particles are close by. And this is the exchange attraction. It comes with the coefficient which is inversely proportional to the mass of the light atom. So it make the light atom lighter, and this interaction becomes larger. Now, the wave function is symmetric with respect to the permutation of the heavy particles. Therefore, all symmetry constraint on the heavy particles comes to the centrifugal barrier. So the wave function should be anti-symmetric. And it gives you a centrifugal barrier with L equals 1 in this case, which is inversely proportional to the capital N. Right? So surprisingly, these 2 effects here, these 2 monotonic curves, when you sum them up, it's not a monotonic. The result is not monotonic. And if you do this for various mass ratios, you get for moderate mass ratios, you have basically the centrifugal barrier. Then the P wave attraction becomes stronger and stronger, and this sum of these two effects develops an attractive well. This is the case of 6.7 corresponding to potassium lithium. Although there is no bound state, and potassium lithium cases, it has many other problems, narrow resonance and things like this, the pure attraction is visible in the experiment. And when you increase the mass ratio up to 8.2, in this potential, there is a bound state here at the threshold. Okay. Interesting is that because of this barrier there, okay, now we're speaking about distances of the order of the scattering length, but it's assumed to be large compared to the van der Waals range. So van der Waals range here is here in this picture. So all inelastic processes, they are forbidden. And there is no second trimer state there, where there is no other states where to recombine there. So it's a elastic P-wave resonance. Now, when you increase the mass ratio further, this repulsive barrier actually disappears, and at 13.6, the three-body problem becomes Efimov. This is the Born-Oppenheimer picture, but the exact calculation basically gives you more or less the same result, and you can also add more particles. So as far as I understand, the state of the art in this three-dimensional business is actually, I recycle my slide from 5 years ago that I used in Santa Barbara. So here I plot the energies of the clusters as a function of the mass ratio. And you have these three guys here. The dashed, the dotted red line is the Kartavtsev and Malach trimer. So it starts from 8.2 and continues up to the three-body Efimov threshold at 13.6. Now the second object here is the tetramer that was first studied by Dmitry in 2012. So this guy appears at 9, at mass ratio 9, and continues to the four-body Efimov threshold studied by this gentleman here. And at that time, I had a fantastic collaborator, Bitsalil. We did this calculation. We had a nice method also. We did this calculation for the pentamer. So the pentamer appears a bit later on the scale and disappears earlier with this 5-body Efimov threshold. So up to like 10% accuracy, you can consider this thing as filling the orbitals, the P-wave orbitals, by heavy atoms, and assume, let's say, that they interact with the dimer independently. So you put one particle, it goes to Px, the second to Py, and the third to Pz. This, it's just, they appear more or less at the same mass ratio, and they scale mostly like, like 1 to 2 to 3 in proportion the energies. And I spent quite some time thinking about how to calculate for larger end particles, and but the trick is actually to go to 2 dimensions. So here I'm abusing a bit the fact that I'm speaking before Xiaolin, but I kind of show you her plot for the structure of the clusters, n+1 clusters in this case. So here the black line is a 2-dimensional analog of the Kartavtsev and Malach trimer studied by Prikopenko and Pedri. It emerges at the mass ratio 3.3, which is quite below 8.2, the 3-dimensional result of 8.2, and this reduction is well described, well explained by the reduction of the centrifugal barrier from 3D to 2D. And now this new guy here, just explored by Xiaolin and her collaborators, is this dotted red line, which is the tetramer. Oh, I forgot to say that this, this trimer has the same structure as the Kartavtsev and Malach, just a 2-dimensional. So this thing has plus or minus, or if you want a dumbbell like this, Px and Py. And so this tetramer, it closes the shell. So it's the second tetramer of two-dimensional p-wave shell. Okay, so it's actually fantastic that it appears at the same mass ratio, and the energies are more or less, you know, twice the binding energy here. And they actually went further, so they went to the next shell, which turns out to be S wave, as far as I understand. So the pentamer is like the tetramer plus an atom in the S wave. I don't know how to show it. It's an S wave attraction between an atom and the pentamer, and this is also continues the work of Jesper and Meira on the tetramer in L=1 case, which is basically the attraction. It results from the attraction of the trimer like this and an atom in the S wave channel. But it's not a ground state tetramer. It turned out not to be. Okay, so in this field, you know, it's very competitive. So the only way to survive is to choose, you know, projects which are as far curiosity-driven and as academic as possible. So we looked at the one-dimensional case. It looks fantastic. So you have, you know, you don't have shell effects, no Efimov effect, easy calculations. Should be easy because all these people with the MRG, the Monte Carlo, there is no sign problem, no problems there. Ideal testbed for various, I mean, you can go from small n to large n. Okay, and the field is basically unexplored in free space and with zero-range interaction. There is just two works. One is Kartavtsev, Malekh, and Safyanos, who considered the Kartavtsev-Malekh trimer in 1D and found that, you know, in this case it's odd parity trimer. It's an attraction in the odd channel between the atom and the dimer, like this. Here I'm using the picture from Meta to show you the trimer. So this is this red dashed line is the trimer energy. So it appears exactly at 1, because at 1 the system is exactly solvable, and you can show that the odd channel scattering mass is infinite. So just a little bit of mass imbalance makes it bound. So Meta himself considered this problem in the Born-Oppenheimer approximation that I just described. So it just integrates out the light atom and solves the problem for the trimer and the tetramer. And that's why, so the statement is the tetramer exists for sufficiently large mass ratio, but the problem is that the theory does not work for small mass ratios because of the Born-Oppenheimer. It has this nonsense here.
Excuse me,
okay.
Can I ask you to speak a little bit up, because your voice comes very low.
Okay. Yes. Okay, I will try to shout. So this is the outline of my talk. I will try to show you very fast our results, exact results up to the hexamer 5+1. And then I will spend some time speaking about the limit n equals infinity. So the Thomas, you know, we consider a few mean field theories for that. And then I will show you what happens when you apply a theory that should not work, where it should not work, and try to, you know, make conclusions so that you don't commit the same errors if you try it. Okay, so we solve the problem exactly by using the STM. So STM is Skornikov and Martirosyan equation, but there you may know some other names for that. In one-dimensional case, it's actually very easy to derive it because it's basically the Schrödinger equation in momentum space using the fact that you have zero-range interactions. So what I need for this talk is just to show that for what function this equation is. So you start with the wave function of the n+1 body. This is the Schrödinger equation. So this is the wave function in real space. So what you do, you place one light atom on top of the heavy atom, and then you Fourier transform the result. And then you use the fact that the total angular momentum is conserved, and you eliminate one, you just eliminate the center of mass. You end up with a function which depends only on n-1 coordinates. And this is the equation for this function. Basically, all ingredients needed to solve the problem is here on this slide. The rest is just technical details. We put it on the grid. We use the symmetries of F. It's totally anti-symmetric. We use the parity, and we arrive up to the hexamer. Wow. So these are the results here. Now we can determine the tetramer threshold at 1.76, and we also determine thresholds for the pentamer and hexamer. So there is not much to be said here. So for any n, you can for sufficiently large mass ratio, the system will be bound. Okay. Well, maybe I will just say that the trimer and tetramer, they have negative parities, and pentamer and hexamer positive parities. Okay, so with our facilities, we cannot go too far above that. So for instance, 7+1 would be too difficult for this deterministic method. And we decided to do the mean field to develop the mean field approach. So the simplest thing is based on the density function that contains the kinetic energy of the light atom, the kinetic energy of the heavy atoms in the Thomas Fermi approximation, just a local density Thomas Fermi approximation. Then interaction is taken in the mean field, and you have also Lagrange multipliers that fix the normalizations. So minimization with respect to the density gives you the relation between the density of heavy atoms and the wave function of the light in a very peculiar manner. So the picture is here. So I plot this phi squared as a function of x. The chemical potential is negative. The coupling constant is also negative. So this guy is positive. You kind of cut it like this. And this thing is phi squared minus the chemical potential is where your heavy particles live. So the square root of this guy here gives you the density of the heavy particles. Now the minimization with respect to phi gives you, and using this previous formula, it gives you the one-dimensional nonlinear Schrödinger equation for phi. Okay, it's like this inside the land of heavy particles and just a free motion outside of this. Okay. So a nice thing about this one-dimensional equations is that they are integrable. You can integrate them twice. Maybe not in the form of known analytic functions, but like in terms of integrals, which analytically depend on the parameters. Like for example, you can make your mass ratio complex or number of particles complex or negative. For the guy who enters into this business, making number of particles negative is not a big deal, really. So, and the result, there will be some number, coming out of it. So, the realistic results are like this. So this is the energy as a function of the mass ratio. The n+1 cluster, n+1 body cluster binds when this ratio becomes larger than pi squared over 36. So for sufficiently large mass ratio. And the wave function looks like, well, it's a caricaturic picture, but it's actually the shape is known analytically. There the chemical potential is 0 because it's a definition of the threshold when the new heavy particle can be bound. And Thomas Fermi size is infinity in the sense that heavy particles, they also occupy, they can also go to infinity. There is no edge. So the energy is proportional to n squared or to the mass ratio to the power of 2/3, and this is what's plotted here, like this. So out of this threshold, you have this trimer, tetramer, pentamer, etc. These guys just branch out of there. And as you increase this parameter, mass ratio over n cube. What happens is that the system develops this Thomas Fermi radius, right? So the heavy particles are becoming more and more concentrated in the middle, and the light one, it exists in this halo state more and more, until, you know, in the extreme limit, the problem basically is the light atom scattering on the potential, which is n times g delta of x, with the energy that, you know, nicely, you know, described in this limit there. So this mass ratio over n cube is the only parameter in the system. That means that, well, this kind of scaling parameter. That means that, for instance, if you increase the number of particles by 2, but the mass ratio by 8, you will get the same shape. You are in the same shape of the function, and also the energy scales. All these curves that I show you, they will collapse to each other if you scale them appropriately. The validity, of course, this is all valid in the where this mean field theory is valid, which is n is much larger than 1. Because the typical length scales, they shrink inversely proportional to n, and in 1D, if your typical length scale becomes much shorter than the scattering length, then it's a mean field limit. Well, okay, this slide shows you, you know, different ways of presenting, you know, it's on how you could present the results, you know. So this is what I'm doing, you know, this collapse. So I plotted energy divided by n squared as a function of mass ratio divided by n cube, okay? And this gray line is the result from the previous slide. This is the Thomas Fermi approximation there. And these results that I showed you before, trimer, tetramer, pentamer, and hexamer. Unfortunately, this idea to show it like this came only today. So I figured out that we lack data here, because we usually worked with reasonable mass ratios that exist in nature, and maybe only 10 or 100 times larger than those existing in nature. But this time you really need to go to 10 to the 4 times n cube, you know, in order to see something. But we'll do that. But before, we did this comparison like this. So we plotted the energy as a function of the mass ratio. We looked at it. We got disappointed. This disappointment comes from the fact that we apply this theory where it should not work, actually. But now I see that it actually, you know, if one of the x's is logarithmic, is always much nicer than you have when you have linear scale. Okay. Yes. So nevertheless, we wanted to, for instance, if we now want to make predictions for 8+1 body system, can we use the mean field or not? So we would like to understand what is the main source of this discrepancy between the mean field treatment. Maybe it's a mean field treatment of the interaction, or the local Thomas Fermi approximation for the kinetic energy. So we can answer to this question, particularly this Thomas Fermi approximation, by going to the Hartree-Fock approach, where we use the variational ansatz in the form of the Slater determinant. We minimize the variational energy, which gives, with respect to the orbitals, that gives you this set of equations for the orbitals. And physically, it's very simple in this case, because we don't have interactions between the heavy particles. It's you know, my heavy particles is ideal gas that lives in the trap created by the density of the light atom, and the light atom lives in the trap created by the density of the heavy atoms. And we hope that, you know, this Friedel type of oscillations will make a difference. We do this, and we get very similar energies, and in the Thomas Fermi case. So we thought that maybe this Thomas Fermi approximation for the kinetic energy is actually good enough. It works well even for n equals 2. Okay. Nevertheless, we wanted to make sure that we have, I mean, we're not mistaken anywhere, either in the exact solution or in the mean field. So we try to make some steps. And these steps are relatively natural. So these Schrödinger equations for the orbitals, they actually give you the whole orthonormal single particle basis. And we can, in principle, increase our variational set, but we actually did not do that, did not go that far. We just figured out that the Hamiltonian couples this variational ansatz, variational state with states V prime, such that we have a single excitation of the light atom and single excitation of a heavy atom from the Fermi C to somewhere to the continuum or to other states there. And if you include this in the second order, which is computationally very cheap because we have to diagonalize this stuff anyway. And by the way, we also did the further corrections I tried to do, but this is all, becomes computationally very expensive. So this simple second order correction gives you the shift of the energy. So these are the results. So let's consider the pentamer, for example. So the gray line is the mean field Thomas Fermi result. You've seen it already. So the dashed line here is the Hartree-Fock. That's what I said, so they're very close. Now, the solid line is the exact, and this trick that I showed you before, it's like Hartree-Fock plus second order gives you this dashed thing here. Okay, so here we are kind of calmed down because we see that we are on the right track. At least, we know what we are doing, more or less.
Sorry, you have about 3-4 minutes.
Okay, good, very nice, very nice. We also consider momentum correlations. We also approach this problem from the theoretical viewpoint. So we try to see the simplest possible thing to compare. And the simplest possible thing to compare is the turned out to be momentum distribution of the heavy fermions, the other than the pair. Okay, well, this object, this F, we get from the STM equation, and we do the momentum distribution. Okay, and it's possible to extract it from all other. So from the STM it comes, as I said. From the Hartree-Fock we have the wave function. We put this thing, we do Fourier, and we integrate. And in the Thomas Fermi approach, this object is just the density, is the momentum distribution of the heavy atoms averaged over the density profile. So, just show you briefly the results of the trimer. This is the Thomas Fermi, it's very smooth, and dotted guys is the exact solution, and dashed is the Hartree-Fock. Here we don't show the Thomas Fermi because it's not bound in this. I forgot to say this. The mass ratio corresponds to terbium lithium, 28.8. So the unfortunate, I don't know, the Thomas Fermi hexamer is not bound in this, so we don't plot it. Okay, so the pictorial summary is like this. So we are on this dimension, number of particles, or mass ratio diagram. We explored this region here. We found that the binding is possible for any number of particles, and we found many things analytically there. So, and the outlook is basically, I would like to come back here, particularly after these results of Xiaolin on this two-dimensional case. I would like to see what's going on there. If I had a bigger computer, bigger brain, or Bezalel, for example, which is the same thing, big brain, big computer. Yes, and the mean field in the two-dimensional case, I would wait for someone else to consider it and to see the results. This is doable because there is no Efimov physics there. Yes, and so in this particular case, it would be nice to know whether there is a maximum number of particles that can be bound before the Efimov in the universal regime. Okay, I've probably done. Okay, so this is the related research, of course, Polaron, and very related research in self-bound Bose-Fermi liquids in low dimensions. In the group of Mariusz, they used basically the same methods as we are. They could actually do the same calculation as us, but they are focusing on something else. And last thing is that there has been some activity in the on the lattice with mixtures with asymmetric tunneling. There you can actually, mass ratio is also a parameter that you can change really. And what interests me is like this DMRG thing that seems to work very well, but I've never seen results on the, you know, this type of problems, if I'm not mistaken, actually. Would be interesting to see if it's possible to use the MRG for this problem. Okay, thank you and bon appetit.
Thank you very much. It was very interesting. Now we are ready for the questions.
Dima, I had one. This is really interesting work. I was wondering if, like for this terbium lithium case, I guess most of the experiments would be probably done in a quasi 1D scenario. If you've thought how tight, for instance, the transverse confinement will have to be to realize it.
Yeah, so, well, yeah, okay, the answer to this question is simple. So you need to have lithium ytterbium scattering length much smaller than the oscillator length. Then you have a bound state which is much larger. Actually, it's not exponential in 1D, right? It's the size is inverse, so it's 1 over the size of the bound state is L squared over A. A is the three-dimensional scattering length. So, as Eric said this morning, you know, if you are ready to work with kilometers of size there, of dimer side of you know, kilometer, then everything is doable. So it's a nice one-dimensional limit. But then, of course, you start asking whether the effective range effects, we would put it on the lattice. This is kind of the next order. This model is nice and shiny, and it has only a few parameters. I don't want to add effective range there.
Are there other questions? I have one. The size of the correction with respect to the Hartree-Fock doesn't look like being different from the 2+1 to the 5+1 ratio. Do you expect that it will stay constant with the number of?
What I kind of think, maybe not 100% sure, but the only thing that Hartree-Fock does not reproduce is the energy of the dimer. So all this, okay, it has the correct structure of the wave function. Parity, for instance, it it predicts very well, and we were ourselves surprised that this happens like this. I assume that it will improve with n. It works very well for 2+1 actually, yeah, as you noticed. No, sorry, wait a second. So here is one aspect. So here at this mass ratio, we're further away from the threshold. There it's probably also important because there we approach the threshold here, and here with Thomas Fermi does not work because we expect in this case this momentum distribution discrepancy at small momentum there. Well, when the new state appears, this is why probably it's a bit cheating because it works a bit. If this thing we would plot at the same distance from the threshold, would probably be a discrepancy there. Yeah.
Okay.
Yeah. For deep, okay. Well, yeah, as I said, I think it's like this.
Is there another question here?
Yeah. Dima, I was wondering, it looks a little bit like, possibly something like the Chevy ansatz. So have you tried to reformulate this in terms of a variational wave function that has different excitations in it?
Wait a second, I will find this. That's a fantastic question. Yes, we tried. So the problem is, that's what I kind of reflected here. The second order, okay, it becomes computationally difficult because the variational space would be of the size n, because you have to know where you take the heavy atom from, so it's n, times the size of single particle basis size, which is basically the size of the grid. Let's say it's, I don't know, 20 minus n, plus times n. So it's a two-dimensional, it's not Fred's ansatz is in free space, so you would have a momentum conservation. This guy would go to p, and this guy would go to minus p, and this is only one dimension, so it's a one-dimensional thing. Here we have 2 and times number of particles, and we tried that. It kind of works, but we are limited to the number of grid points. And we tried the third order. Yeah, so I answered, I think. Yes, so it's basically some kind of Chevy ansatz, but unfortunately in the inhomogeneous case, it's kind of as what I explained. So it's twice as big. Actually, we also thought, okay, fine.
Actually, maybe can I follow up? So when you say inhomogeneous, you mean that it's not the infinite system? Because, or
yes,
do you mean that you have a trap? You don't have a trap.
I don't have a trap. I don't have a trap, but okay. So, well, honestly, I think that. Okay, let me answer that first. Okay, so this construction on top of the Hartree-Fock ground state, you know, these orbitals that come from there, it seems reasonable from the viewpoint, at least if the system is bound, it is bound. You don't have the states that are all over the place and the continuum that plays no role there. This is already a good sign. But if you ask me, how would I approach this problem with 20 plus 1 or 10 plus 1? I would probably think about some kind of Monte Carlo or DMRG type of thing, which is like a black box, and you know, you just run it and it produces something. Because here, yes, sorry, I'm fluctuating. So, inhomogeneous is in the sense that, okay, I repeat, with the Chevy ansatz, the states would be also of this type, but there will be a momentum conservation. So when interaction happens, you know, here, the light atom goes here and the heavy atom goes there. So it's with p and minus p. And this is a configurational space which is one-dimensional because it's just p. Here in my case, it's nu and mu, and all nu and all mu are possible. So it's a square of this matrix. See?
Thanks.
So
I
would just search for another method to solve it for up, you know, above 5 plus 1. Sure.
Okay, I have a question. Thank you first for the talk. I know that for the case of bosons, there had been an experiment like a few years ago, and to show the difference between few and many by comparing, I think, the many particle solution to the few particle solution, and they, I think, concluded that around 5 particles, the results were indistinguishable from the many body predictions. So I wonder, could you relate your deviations between your few body and many body approach to their deviations?
First of all, I'm not sure whose experiment is that.
I think it was from a group of Heidelberg, but I could mix it up in my head.
Cesium lithium?
Yeah, it was
Matthias?
probably the
Matthias?
fermionic experiment
Ah.
as opposed to the bosonic one, Andrea.
I don't know. I have to look at this. I mean, it depends on how. Okay, here there is no. Okay, here it is. The problem is non-perturbative. What I'm doing there is just against the rules. You know, I'm applying it. Motivation was just to make sure that two limits kind of cross-check between the two limits, and we are kind of very far away, and they kind of look like this. And we search for this correction. Just peace of mind. But of course, okay, from the viewpoint of the maybe I'm not answering the question. But I don't know how to answer it. But for instance, predictive power. Like for instance, we want to study now n+2 problem. Okay. Qualitatively, this mean field works for 5+1, 4+1 even. If there is an effect that the mean field predicts for 7+2, or I don't know, if it's an interesting effect, then at least we can field, first step towards this effect, and then we would do sufficiently motivated, we would do exact calculation. So it's with this motivation, I would just use. I personally also like the Thomas Fermi theory because it's analytic. It's fantastic. If I answer at least partially.
Thank you.
Last week we had some observation in a seminar that one-dimensional world and two-dimensional worlds are completely different. What is your opinion and what are your plans to go to the two-dimensional?
We actually did some preliminary count. We started from 2D, but we actually did the halfway of this tetramer. So Xiaolin, beat us a lot. And then we kind of switched because the mean field theory works for 1D as well. 2D, the mean field theory in 2D is a bit more ugly because of this cutoff dependence. So it's not really the mean field in 2D is more difficult. There is something to extrapolate to, effective. You need some cutoff effective range, and this is. But yes, 2D and 1D. 1D is completely counterintuitive. You can forget about everything that you learned in higher dimensions. It's better if you forget, because otherwise you're in trouble. But in this particular case, we are fine because the system shrinks and get into the mean field regime, and the mean field regimes are fine. So we are good. We are not in the strongly interacting regime. And the difference, as I said, is shell structure. Here we don't see even odd any kind of even odd correlations.
Okay, thank you. I don't see any other raised hand. Also, they are not. So I think we can close the session. Thanking again our speaker.